In Unit 5 of Kinetics, 5.10 is called the multi-step reaction profile. You may have had reaction profiles in the past, which look more like the ones that are on the left here. And we'll start with those as a review, whether you had them in Unit 6, or in a unit, maybe in a first-year chemistry class. But typically, students come into Unit 5 having some background in these energy profiles that are on the left. And then on the right is really what this new section 5.10 is all about, which is the multi-step reactions when there's a reaction mechanism. All right, so first off is going to be, how do we classify the ones on the left? So it's just a little bit of a review. So on the left, which one is basically endothermic, which one is exothermic, and then why would you say that? Sometimes on the AP exam you have to justify your answer. So the first thing is that from here to here, these are the reactants and these are the products. And then the activated complex or transition state is at the top. That's where it's not a reactant, it's not a product, it's in literally in a transition of that. And then the change in enthalpy here is going to be, in this case, negative. So that's going to be our exothermic graph. And then it's going to have a change in enthalpy. So if you haven't covered that yet, because maybe you have not done Unit 6, this is called a change in enthalpy. And enthalpy can be converted into heat quite easily. So most time it's a change in heat of the reactants and products, or in energy. Same here, reactants, products, there's a transition state or activated complex. Depending on what book you have, they'll use different terms. And from here to here, you have your change in enthalpy. And so this is going to be your endothermic reaction with a positive delta H or a change in enthalpy. So energy has to go in for that reaction to occur. The other thing I'm going to mark off here is something called the activation energy is from here to here or from here to here. So that is going to be called the activation energy. I don't have a lot of room to place that. And that's the energy required for the reaction to proceed. And it's one of the requirements of the kinetics actually working is you have to have enough energy put into the system for the bonds to break. You still have to have correct orientation, but this activation energy is the energy that the particles need to collide and break bonds. All right, so let's move on to then how are these a little bit different for a multi-step reaction. So this is when the reaction has a mechanism where there's more than one step. So first off, we can still label some of the same things. Which one's endothermic, which one's exothermic? How do you find the change in enthalpy? And then what are the different activation energies? And then how many steps are there? And last but not least, which step is what's called the rate determining step, meaning it's the slow step. All right, so on these two, if we're going to compare these two over on the right, again, we can say that one of them is endothermic, one is exothermic. So just kind of ask yourself which one do you think is which. So from here to here is our change in enthalpy again, or from here, kind of like here to here, is our change in enthalpy. Sometimes it's a little hard with these multi-step curves to see, but it's from the reactants to the products. So same thing again, reactants to products. And there's a lot more we can label on these graphs. Okay, so I'm just going to kind of erase these little dashed lines a little bit, just because there's going to be quite a bit we're going to add to these graphs. So the next thing is going to be who is exothermic and who is endothermic. So if you said this one was positive and that was our endothermic, you would be correct. And then this one is our exothermic. And again, this one would be the, endothermic means a positive energy, and then this one would be a release of energy to the surroundings. And that, again, you'll cover in Unit 6 if you haven't done that yet. The next thing is going to be where are all the activation energies, and then how many steps are there? So first one I'm going to do is say like we have a transition state here and another transition state here. So we can call it transition state 1 and 2. There's also going to be what's called an intermediate right at this point right here. So this is going to have 2 steps, it's a mechanism that has 2 steps. And then the intermediate is at that, kind of like that area in between those 2 curves. And then the activation energy for the first step is here. So we're going to call that EA1. And then the activation energy for the second step is from that intermediate plateau-ish area. And I'll have to put that one over here. And then that's the activation energy for the second step. So what you'd write down to is that this has two steps in the mechanism, or 2 elementary steps. I don't have a lot of room to write, but they are called elementary steps. I'm trying to spell the word mechanism correctly. Sometimes it looks one way. Okay, there we go. 2 steps in the mechanism. And then the other thing you're going to want to say is that step 1 of this mechanism is the rate determining step. I'm going to put RDS. You might see other teachers that use RDS as a shortened term for rate determining step. So again, I'm just going to write that down here. So if I write RDS, that means the rate determining step. And that just means it's the slowest step in the mechanism, and it's going to control the rate law for that reaction. So for step 1, that's where we're going to get the rate law. So that's the other thing I want to remind you, and then that's a previous video, is that the rate law will be written from that rate determining step. All right, for the next one, you'll end up having 3 different transition states. So there'll be three steps to this mechanism. So that's transition state 1, 2, and 3. And again, they can also be called activated complexes. And then you also will have their own activation energy. So this one would be activation energy 1. And then from here to here would be activation energy 2. And then this one would have a really low activation energy. Tried to make sure all 3 of these were different. So again, this first one, I'll see if I can sneak it in here. It's going to be really small. So this is activation energy 1. This one is activation energy 2. And then this one is activation energy number 3. And again, you have to decide which one of those is then the rate determining step. And the rate determining step is always the one that has the highest activation energy. So in this case, we're actually going to say that there's 3 steps to the mechanism. So there's 3 steps in the mechanism. And that this one, step 2, is the rate determining step. So maybe this is where one of those steady state approximation questions where the first step might be go to equilibrium, be fast. And then the second step, you might have like that intermediate to deal with that you'll have to maybe use the first reaction to substitute in to get your rate law. So the other thing is there's an intermediate 1 and like an intermediate 2 at least in here at those lower plateau areas. All right, so let's move on to an example problem. So down here, I've kind of given us an example problem that we're going to use to practice this. And in this example problem, we have the molecule hydrochloric acid, but we'll probably just say hydrogen chloride because it's a gas. I didn't put the state of matter. And then you have the ethene molecule. This is almost like a beginning to organic chemistry. And you're going to put the hydrogen and the chloride atoms onto that ethene molecule. And then if you notice, you broke that bond. So they believe that when this hydrogen chloride molecule collides with an ethene molecule, you'll have this intermediate that's actually both. Okay, those are going to be our intermediates, plural. And then they have to collide, and then it'll actually produce that product with that double bond being broken, and then the hydrogen and the chlorine as atoms placed onto that organic ethane molecule. All right, so with the graph that's given on the side, you have to then decide these 3 questions. Which one's rate determining? What's the expected rate law in the overall rate order? And is this reaction endothermic or exothermic? All right, so let's just kind of get going with the questions. I'm just going to switch to a different color here. I'll switch to blue. And the first thing you want to do is start labeling everything that you can, okay? So we have our reactant here, our product here. Start with that. You have either an activated complex or a transition state. So again, you can use activated complex or transition state. And that's going to be number 1. And then this is going to be transition state number 2. There will be an intermediate right here. So some kind of in-between particle that where they're breaking and making bonds. They're not quite complete. You're going to have your activation energy 1 right here. And then from here to here is activation energy 2. And then last but not least, you can always start from the, and I'm just going to dash it here. From the start to the finish, your change in enthalpy is going to be right there. All right, so you can label kind of all those things on the graph. And then if you think about it again, our intermediates, I'm just going to kind of circle this molecule right here and the chloride ion both show up in step 2. And so which of these, step 1 or 2, is the rate determining step? And again, you base that off of whichever one has the highest activation energy is that rate determining step. So you'd say step 1 is your rate determining step, is your RDS. And if you had to justify your answer, you'd just say because the activation energy 1 is greater than activation energy number 2, if it was short and sweet to the point. but basically more energy has to go in to break those bonds, so it's going to be what controls the speed of this reaction. All right, next, what is the expected rate law? So if you look at it, we can use what's called that molecularity from a previous video in the section that we covered that. So we don't write the rate law for that overall reaction. We actually will write the rate law for the reaction that we have here. Now, this is one of the few times where it looks like the same thing. So this I wanted to cover this example is if we write the rate law for this overall reaction, it is going to look like it is the same for this one, but there are actually two steps to this reaction. So the rate law is going to be rate equals K, and we're writing it based off of step 1 because it is our slow step. Now in another section, it would actually say like on the side, I'll have to put it right here, they would call this slow, and then they would say this is fast. But in this case, we didn't have that when this question started. We only had the graph. So then you're going to say it's rate equals K to the hydrogen monochloride or hydrogen chloride gas particle, and then the ethene particle. And again, if this is kind of confusing to you, this is just saying that the carbons are attached to each other with a double bond, and then the hydrogens are off to the side. So that might be something new to you. You've not seen a molecule written that way, almost like how organic chemists will write the molecules. And then that one would be also to the 1. So these would be first order with respect. So this would be what's called first order with respect to the HCl, and this one would be first order. And again, we're really truly using, it's a little misleading that this one, we are using that step 1 as the rate determining step. And then overall order would be second order overall, because you just add the exponents. So it's just, you know, overall order, you just say is exponent 1 plus 1 is how we get to 2. So just kind of show that quickly, just in case you haven't been good at that until this point at the end of this unit 5. All right, last but not least is it exo or endo? So if you look at the difference in the reactants and products right here to here, you will see that this is a exothermic reaction, and it's an exothermic reaction because the change in enthalpy is negative, and you could also say the products have a lower energy than the reactants. I'm going to go fast there. So it's exothermic because the delta H and the products, so P is products. Okay, so if you don't want to write P, you'd say products. So end products have a lower energy than the reactants. So energy is released, again, to the system. The system releases energy to the surroundings. All right, so that's 5.10 with multi-step reactions. So you could maybe have to label the different parts of a multi-step reaction, or you could use it to predict the rate determining step. The mechanism that might be occurring will be given then to you, and then writing the rate determining step, the rate law that might be predicted, and then if it's exothermic or endothermic.